we have a lot to cover. For distributed systems reference architectures, my name's Tim Berglund, in case you don't know that. I work at DataStax. We are a distributed database, distributed data platform company. What I do is I help you learn about it. My team, I have a couple of teams, few functions that report to me. One is curriculum, and so the people who make the actual curriculum that teaches about how to use Cassandra and Spark and how all these things integrate with our product. That's my team. I've got a web team that makes a website called DataStax Academy. They do a great job. And also a video team. We make video curriculum and sometimes cute little short films that are educational in orientation, and that's really the fun part of my job. So the most fun part. Given that, that's actually an important disclosure, because I'm here talking about distributed systems, and I'm a guy who works for a company that makes distributed systems stuff, so you should be, all of you, not at all surprised to hear Cassandra come up a lot in this talk. That should shock no one, because that's really what I've been spending most of my time on for the last 2.5 years, and it pops up. So, I want to give you 4 canonical examples of ways to build distributed computing and data storage systems that are different approaches. They've got different decisions they're making, different utilities they're trying to optimize. But all of them are real things that are being used right now with various levels of hipsterness. And I'll talk about as much as I'm able to, examples of how they get used and really what makes them tick. And for each one, also, just to make this a little more interesting, I'm going to pick, for 3 of them at least, pick a technology that is kind of central to that approach and give you a little overview of it. So like we'll talk about Kafka, we'll talk about Cassandra and things like that. So if you don't know those things, you'll get the 5-minute intro version of those. So you should leave with an idea of 4 different ways to build your next highly scalable system, mobile app, website, Internet of Things, network, whatever it is, and a few of the technologies that support those. So that's kind of the goal. And as long as that's what you want, you are totally in the right place. And I think we have until 12:50 to get this work done. Now, I would also like to give you a little bit of a definition of what I mean by a distributed system, according to the great and, as of last year, late Andrew Tannenbaum. A distributed system is a collection of independent computers that appear to its users as one computer. Amazon.com, distributed system. Cassandra database, distributed system. My MacBook Pro. Well, 3 characteristics in the definition that I use of a distributed system, just to get us started. One is the computers operate concurrently. Definitely true of Amazon, definitely true of Cassandra, definitely true of this computer right here. There's a computer in the camera, there's all kinds of computers down here. There's not just the Intel processor, but there's all kinds of processors operating concurrently, failing independently, pretty reliable machine. Haven't experienced any failures, but certainly any of those processors could fail. Any node in a Cassandra cluster could fail. As a popular distributed systems Twitter personality said the other day, if you've got a distributed system on the scale of thousands of nodes, you've always got failures happening all the time. That's just a thing, and they fail independently of one another. The key thing, and this is a little academic, this definition is required for some theorems that get proved about what you can and can't do in distributed systems, is that they don't share a global clock. And that's why, I won't go into detail, but that's why I don't consider my MacBook Pro a distributed system. I would argue that the processors, in any meaningful way, really are synchronized in the way that they interoperate. But certainly the 48 cores that I have in any given node in my Cassandra cluster, those clocks are not synchronized between one server and another. So that's a key thing. The computers don't share a global clock. But a bunch of computers, they operate independently, they fail independently. That's what I mean by distributed. And then we get into the actual engineering. How do we build interesting things out of these computers? I'm going to show you 4 examples. I'm calling them reference architectures. Somewhere reference architecture ends and pattern begins, and that line I think is a little fuzzy. But this is really what we're going to do. And there are 4 of them. I'm calling them the modern 3-tier distributed system, the sharded system, the Lambda architecture, and the serverless architecture. A distributed system using no computers at all. It's a joke. So, it's all right. It's all right, I understand. Let's just go through these and look at them. Now, I cut my teeth as a programmer in firmware. I was an embedded systems developer. I got my first job in the early 90s as a college student, and it was freaking awesome. I loved it. I got to debug software with an oscilloscope, you people, and an X-Acto knife, like cut traces on a board. I miss it. There's no going back, but those were great days. Loved it. When I, towards the end of the dot-com boom, with my impeccable timing, as always, I entered the world of the internet, left embedded systems behind, and entered the at that time, very exciting and new and fresh Java world. And 3-tier architecture was this new thing. The EJB spec was still pre 1.0 then, and people were talking about these 3-tiered systems where you've got, what'd you have? You had a presentation tier, a business tier, and a data tier. And this was how you built your site. This was the right way to do it. It was a new and hot pattern. And you know what? This is not a horrible thing. This is not somehow a bad idea. What went wrong was some of the technologies, right? Because back then, in the late 90s, early 2000s, basically, you used Oracle, and we had this thing, and that was a problem, and it didn't really work out so well. And so there was a certain amount of madness that entered the picture. It's so bad that you actually lose the display. That's how bad it was. And you're better off just shutting it off and going home. No. That's what we had. The database was big money, and the business tier, that didn't really scale. It wasn't in any kind of contemporary thinking about how to build a distributed system or scale horizontally. It just didn't do that. People talked about it being a technology for that, but it didn't really do anything. But again, the basic pattern is not bad, and this still happens all the time. Let me change the names and not meaningfully change the diagram, and all of a sudden, this is cool. Okay, it's the same architecture. And I don't think that this is foolish, okay? I don't think that merely because we have moderately hip technologies there, and let's face it, Walmart.com is built in Node.js, okay? This is no longer some sort of incredibly cutting edge thing, which I guess that's not fair. Walmart actually, they do tend to do some rather cool things, but this is becoming a mainstream enterprise technology, so it's not like it's that hipster, but the basic pattern here is pretty solid, and we can build interesting things this way. But let's take a look at the way we would actually do this in real life. And by the way, in the scope of this talk, I'm going to say things like Node.js and React, and we'll just leave them as they're out there and they're there. We won't deep dive into those at all. That's kind of not our purpose here. But, oh dear, I am using a little bit too much of the width. Like in broadcast TV, there's this bounding box. You have the 16 by 9 thing, and there's this box that you're not supposed to go outside of because you never know. I went outside. It happened. So anyway, those are clients. Those are just browsers out there. And there's an internet, and they're going to come into some sort of proxy. That can be Amazon Elastic Load Balancer. That can be Nginx or whatever. And then I can have multiple node servers and that Cassandra database on the back end. So realistically, that might be the thing that I actually build out. That is, let me draw the lines, not meaningfully different from the thing that was super cool and about to happen in 1999, when the year my youngest was born. So that's a long time ago now, but it's essentially the same architecture, just with some names changed. That's why I call this modern 3-tier. We build systems like this, and it is not a thing to be embarrassed about at all. if you fielded that, I think you should feel pretty good about things. And again, like I said, to an approximation at this level, Walmart.com, React front end, Node.js. You don't say business tier anymore, but I'm going to say it. Node.js business tier. And in principle, same thing. And they do actually use Cassandra, and I don't know exactly what parts are what in detail. They're DataStax customers, so there's some DataStax Enterprise, the commercial version on the back, so that database is actually there. As promised, for each one of these, I want to pick some technology to pick apart a little bit so you can learn some specifics. So for the modern three-tier architecture, which is a respectable approach to building scalable websites and mobile apps, let's look at Cassandra. Now, Cassandra is a distributed database, and some cool things about it is that it is entirely peer-to-peer. Every node is the same as every other kind of node. The same kind as every other node. There's no master or metadata controller or anything like that. They're all peers, but we do uniquely assign them different numbers. Each has a number, we call it a token. And usually you draw a Cassandra database as a ring. Now there's nothing physical about that. There is no ringness to the way they're wired. They're connected on an Ethernet network, just like any respectable server in any data center. But for good reasons, we draw them in a circle like that. And you can see I've got these nice tokens. In real life, they're 64 bits long, but this is the special 16-bit Arduino version, I guess. 2,000, 4,000, 6,000, 8,000. There's this token space. And I'm going to use that token space to figure out where to put things. So one of the problems in being a distributed database is, well, the problem is I have too much stuff to put in one place, and now I have to decide where to put my stuff. And so we use those tokens and a hashing function to decide where to put things. Now, the Cassandra is not a key-value database, but to a very high level of abstraction, you can treat it like one. And it's useful to think about it like one when you're just getting to know it. So for the purposes of our 5-minute treatment of Cassandra today, let's call it a key value store, even though it's not one. Just a few days in this time zone, drinking a lot of coffee, that jet lag, killer. My jet lag peak hours, for whatever reason, they start like at about 1 p.m. So you will see me drinking coffee. So I'm thinking coffee here. Key and value. What we do is we hash the key and keep the value, and this hash value, 9F72, is going to fit in this ring between 8,000 and A,000. And that arrow means if it's bigger than this and less than this, it's going to go to that node. So I'll write it there. And then later on, when I want to read that key, stepped on some audio infrastructure there. I hash the key, and that tells me, I'll go to that node A,000 and pull the stuff out. Pretty simple. So that's the basic idea of how you put things into Cassandra. All kinds of other questions about like data model and interesting things there, we're just not going to get into. But one other thing that we kind of do need to treat, you would not want to have just one copy, right? You'd want to replicate. There are various ways of doing that. The simplest, if our cluster looks like this, is to say, well, let's put the first copy there and then just go to the next 2 nodes in the ring and put replicas there as well. Now, as is always the case with like any distributed systems problem that I have looked at, anytime you solve a problem, you create at least one more problem. It's basically, I should have started with that. It's basically terrible, and you're in the wrong room, and you should go to a talk on how to build small systems with easy to understand tools, because you'll have more time to refactor and you'll go home early. But you're here, it's too late for you to leave. Distributed systems are always hard. And you do something like this, this can change, right? This is, we'll say it's my default coffee order. That's mutable. And once I've made copies of mutable state, all kinds of bad things happen to me. And Cassandra fortunately has elegant answers to those. Like, what if, when I go to read the replicas, what if they disagree? Ooh, what do I do? When I go to write them, what if one of them's down? Is that a successful write? When I go to read them, what if I can only hear from one of them? Should that count as successful? All of these are questions that come up when you're playing this game of making copies of things and copies that change. And there are answers to all those. That's kind of the Cassandra deep dive that we won't get into. So that database, that basic pattern, that consistent hashing thing, pops its head up and is kind of winking at you in various tools. We'll look at Kafka later on. Kafka uses a similar technique to get its work done. And Cassandra proper is showing up in a lot of places. This is a good database to have some rough familiarity with. All right, back to modern three-tier. What are the strengths of the modern three-tier architecture? Well, as I have drawn it, and I think we should make this a requirement of the pattern, is we have a rich front-end framework. Now, in the old days, the first time as Java developers, if you were doing this 15 years ago, we did not have rich front-end frameworks. AJAX was not even far from being an obsolete term. It wasn't even a term yet. And so you didn't have a lot of this. You just had static content on the front end. Most of the ways people are doing UI these days, we have interesting frameworks that do lots of work in the browser. The browser is where a lot of our application takes place now. And we think that we do that because we want a rich and responsive user experience. We want the page to be able to move quickly. We want people to be able to do a lot on the page without rendering whole new page loads and all that kind of stuff. That's what we tell ourselves. But guys, we're also buying some scale. There's more computation that you've pushed into the client, and that's a good idea because you've got all those darn client computers out there everywhere. And the more of your app you can have there, the less you have to have on the server. So rich front-end framework, it is not accidental that I put React up there. That could be any of the current crop of JavaScript frameworks, but there should be lots happening in the front end in this pattern. We have a hip and scalable middle tier. It doesn't even need to be hip. It can be Spring. I love Spring. I think it's amazing. I'm a Java guy. Spring would be my sort of go-to more than Node would. It's not all that hip, but it's also scalable. So that middle tier, whether it's hip or not, is scalable. And the data tier, as I've drawn it here, is I'll say basically infinitely scalable. It's probably going to scale more than your app is going to need. If we have a modern scalable database like Cassandra back there, that's going to get big enough. And you don't have to worry. In the old days, that was the thing that fell down first. Like we could figure out how to cluster Tomcat or how to cluster web methods or whatever it is we were doing in the middle tier. That was difficult to cluster, but you could do that. Databases were always the thing that fell down first. And now we've got options on the far side of the back end that get us out of that. So this old architectural pattern, I really think it has all the life in it that it needs. And it's a very, very viable thing to do. I mentioned Walmart before. I almost randomly picked React and Node just to illustrate frameworks on the slide. They've got this framework they've open sourced called Electrode.io, which is a thing that they've used to build Walmart.com. It's JavaScript, so it has to be a framework. We don't just keep the tools we have. We build frameworks out of them. It's like what Java people do with logging. We always have to have a new logging framework, except we take 2 years to build new logging frameworks. JavaScript folks take about 2 months to build new frameworks. It's just the culture. So that's how it goes. That's Walmart. What are some weaknesses? If state should creep into the middle tier, that can be a problem. So you want to make sure if, for example, if it is a Java middle tier and you've got the servlet API lying around and you've got a session using stateful middle tier things, it is a temptation. and that's going to limit the ability of the middle tier to scale. So you want to try not to do that. And there are some frameworks later on that actually tie your hands that we'll look at. When we look at serverless, you simply don't have the option. And so you have to solve state some other way. I've got a rating scale for each one of these architectures. We've got scalability, hipness, and difficulty. I couldn't decide whether to call this maturity or hipness. Those would be inverses, right? So maturity would be probably a good thing, but it would be the inverse of hipness. Now hipness, there are also some good things about it. So I'm going to say 4 out of 5 on scalability, 2 out of 5 on hipness. Also, once I thought I was going to show that guy for the rating, there's no way I could call it maturity. I had to call it hipness, right? That was pretty much done. And 3 out of 5 on difficulty. Not too bad. There are some things, like if you're actually using Cassandra on the back end, there's a learning curve there. It's not a relational database. You have to learn some new things. So once you enter this world, there's a little bit of a learning curve, but not so bad. Okay. Checking my time, 25 minutes. We're at the halfway mark. 29 out of 126 slides. It's going to be fine. It's going to be just fine. Actually, it will. A lot of those are poor man's animation, so don't fear. Okay. Sharded. I guess I missed that. We're going to call this the sharded architecture. And the basic idea here is that we've got, this is what we have when life is simple. There's some client, there's this complete application that exists as a monolith, and there's a database. And that's great. Once again, if you can stay there, if this is the size of your system, life is good. Maybe you're not going to get a conference talk out of it, but you go home on time. Don't feel bad about yourself. This is a preferred way to live. But when clients proliferate and there is more work to do, that single database and that complete application in one place are not going to work. So what we do, the essential idea in the sharded architecture, is that we take complete chunks of application and we reproduce this application database thing. Examples of this, Basecamp would be a famous one. Slack, my best understanding of Slack's architecture is that it is properly a sharded thing. The database that Slack uses, I already told you it was sharded, so you'll guess if I ask you, but it's MySQL, which blows me away for how, their runaway growth and how big some of the teams are and all that kind of stuff. But if it's sharded, you can make that work. So you have a complete chunk of application stack with a singular and potentially not all that scalable database, and it works. So when can of course, in between there, I don't have all the work done yet. I have to have some kind of routing. All right, my requests are going to come into some kind of proxy, and in the previous slide, I had specifically called out Amazon Elastic Load Balancer or Nginx or something, a classical reverse proxy kind of thing. Here I'm saying router because there is probably some kind of HTTP proxying going on, and sometimes also some lookup. So we tend to sprout a little Redis down here. You get a growth of a Redis. That's a nice quick way for some front end to look up, oh wait, which shard am I on? Something like that. Those little extra appendages will grow there. Will have a tendency to grow there. They don't need to necessarily. But again, the basic idea is simply that, of breaking up the application into pieces. And each piece is this simple, bucolic country life where everything is nice and easy. When does this work? Seems like you should do it if you could get away with it. Yeah. Yeah, when the shards are really independent. So I said Basecamp, I said Slack, eminently shardable businesses. So that's the right thing for them to do. Those shard nicely because you get these organizations or clients or customers that will break into pieces like that. I don't know many specifics of Salesforce's internal architecture. I suspect if I did, I would. It's a big and old system, and so it's probably one of those things. Even though it's very successful business and very talented engineers making that thing hum, it's probably big enough and old enough at this point that if I did know something about Salesforce's architecture, I would run screaming into the night. It's hard to be a big site like that for that long and not grow some hair. But again, that's an example of a business that would be a kind of site that would be very shardable. So why does sharding have a bad name? It's another one of those things. My first two, I'm saying, well, 3-tier, it's great. Stop hating. Do 3-tier, you're doing it anyway. And I say sharding, it's fine. If the service or business supports that kind of architecture, do it. But I think we're kind of programmed to think, wait, sharding is difficult and it's bad and it's going to bite me for some reason. Maybe that's just me because I'm the Cassandra guy and I'll often talk smack about sharding databases. Let me tell you why. So let's dig into that. Here is when sharding attacks. So database sharding is probably a bad idea. Sharding as an application architecture, as this pattern of distributed systems architecture is good, but as a database thing, bad. So here is my single server database. Life is good. At some point, when scale increases, I run out of gas and I do read replication, right? So now all of my writes will get sent here and I can load balance my reads to these copies. This is an eventually consistent system now, and I don't have very good control over that in this kind of system. Let's say these are Postgres's or MySQL's or something like that. And how do I know which one is the leader? Well, probably just like the router, probably Sprouted or Redis. If you develop a Redis growth, you don't need to see your doctor. I think it's fine. All right. This, as if straight from hell, we'll get a Zookeeper. I shouldn't say that. Zookeeper's great. All right, it does certain things very, very well. But when you see it pop into a distributed system like this, to me, this is a smell. Smell of brimstone, yes. This is a smell that something might go wrong. So you can use Zookeeper to do master election. And I won't go through, you can Google that fairly easily. There are some data types in Zookeeper that make that super easy. But let me show you where this goes south. After we start read replication, okay? We've got those read servers. We load balance reads to those. We've got a little bit more gas out of our database. We grew a Zookeeper. See your doctor, get it checked out, make sure it's okay. After that ran out of gas, then we sharded, okay? And this is why sharding has a bad name. This is a thing people do, but this is to grow your database. This is not the sharded architecture I just showed you. This is when I've got one big application cluster that's presenting my one database server with too much load. I do this to my database server. I don't shard the whole application. I just pick a shard key and say, well, users A through F are on shard 1, G through N are shard 2, and O through Z, that's how many people say it, are on shard 3. This can be a problem because, again, once you've got enough nodes, you will experience a condition called a partition. This will happen when some of the nodes suddenly can't see some of the other nodes. So imagine along that red line there, the nodes above and to the right of that line, they can all see each other. Below and to the left, they can all see each other, but the two partitions can't. What's going to happen? You're going to say, oh no, I can't see the leader node. Let me go talk to Zookeeper and we'll elect some new leaders. And then the partition goes away. See, flames there, it's terrible. The partition goes away and you have madness. Okay, this has happened. This has happened in Europe before when there was a pope in Rome, there was a pope in Avignon. Bad deal, guys. Okay, you don't want this. So database sharding has a bad rap for a reason, and don't let that poison you to the notion of sharding as a reference architecture, as a pattern for building a distributed system. If the business, the service, whatever, allows that, it's a perfectly fine thing to do. So, strengths. We can isolate clients from one another in terms of data. Like there might be regulatory reasons where you can't do multi-tenant or something like that. You just can't do a multi-tenant schema. They have to be on separate servers. Maybe they have to be in separate geographies, in separate sovereign geographies. That is easier to do when you've sharded. It's also easier to isolate deployments. I might run one version of the service for one client, and then there's another client that pays us lots and lots of money to run the version from 5 years ago, and you try to tell them it's a bad idea, but they make you because it's lots of money. You can do that. This is an advantage of the system. There really isn't anything crazy. You're building the system that we all know how to build many times in parallel and adding the router in front of it. So it's pretty simple technologies. However, we can still build some complexity. We see that emerge with the Redis routing layer, and there are some other things that we'll look at, if there's time at the end, that kind of have to grow up. For example, all these shards are probably going to want to log to the same place, right? At least security ops is probably going to want a common log of what's going on everywhere. So you've got your independent shards. You're still probably going to have a logging framework that's common. So the picture gets a little more complex than the diagrams that are nice and fit on one slide. Analysis across shards is impossible without some kind of ETL process and integrated analytics database. So if I want to see trends across all customers, seems reasonable, I'm going to have an ETL process where I pull that out and dump it into some other kind of database. And the some other kind of database for analytics is very reasonable. The ETL is also time-tested, uncontroversial practice, but it's a bummer. You'd rather not have ETL if you didn't have to, so that's undesirable. Also, what if one shard gets too big for the hardware you deploy? If you have an oversized shard, that's a bummer. The theory is probably most of your users are small enough to aggregate many on one shard. That's probably how this works. And if you look at companies like Slack and Salesforce and all them, obviously they're going to be reusing infrastructure like crazy. That'll be multi-tenant either through virtualization or through containers or something. But when one of those users gets too big for a shard, that runs you into the need to go to some other scaling paradigm to fix that problem, or scale up in expensive ways. So if you outgrow a shard, that's a bummer, and that will cause madness. And there may be, what am I illustrating here? Analytics. You could be doing something like this, right? You've got all of this customer data in all these nice relational shards. I might dump that off into some kind of clustered database. I could put it in Elasticsearch. I could put it in Cassandra and use the commercial search stuff, or whatever I'm doing there. I put that someplace to analyze. I could put it into HDFS even and run Hadoop jobs on it because the fancy struck me and I wanted to do that. Actually, I wouldn't do that, but maybe there's definitely good reasons for it. Okay, scalability. So I'll give it a 3 out of 10. Works well when it works well. Then it does bump into limitations. So not perfect. Hipness, not even a little, right? This is doing everything the old way, just doing it a whole bunch. Often, that is wise. Often being clean shaven, figuratively speaking, is the right approach. Difficulty, I give it a 4 out of 10 because a lot of the things that we need to do, we still need to come up with ways of doing them. They're all technologies that we understand, but we're still going to grow hair. We're still going to need to, the slice of application functionality is nice and simple. That's all great, but I still have logging. I still have analytics. I still have this router, all this other. I've pushed complexity out of that slice. and it pops up in these other places. So it doesn't necessarily manage complexity. All right, Lambda. I'm just looking at my time and thinking about how to proceed. We're going to talk about Lambda. So normally Lambda comes up as a way of handling streaming data. The assumption is that when you're using the Lambda architecture, I'll show you a picture and I'll define it in just a minute, but if you've heard of it, you probably know this comes up when I've got streaming data. So I've got these events that I'm processing that are coming into my system and they never stop. And the way Lambda is traditionally defined is to say, well, I've got my stream processing and I've got my batch processing, and these are different kinds of things. And it's hard to build one system that does both well, so what Lambda does is it builds both systems, all right? I would encourage you to get away from streaming and batch as terms and move to bounded versus unbounded. Batch is really bounded. That means there's some data and it's here. It's there and I know how big it is, I know how many things are there, or at least I can go to them and count them and add them and average them and stuff. Unbounded means it started and I'll stop when I stop and just data events are coming in and I'll process them. So unbounded is the new stream, bounded is the new batch. Very, very good podcast here. The URL's in the slides. Slides will be on the website later. On Software Engineering Daily, it's an interview with Frances Perry. She nominally is talking about Apache Beam. They actually don't spend much time on Apache Beam, but there's an incredibly cogent discussion of stream processing. And I envy her interviewing skills. Very, very clean, good, precise answers, worth listening to. It's a good podcast anyway. If you don't know it, you should listen to it. It's a good one. Okay, so you would use Lambda when you have unbounded immutable data or events. You are processing events. There are tweets, there are log entries, something is happening and you need to process them. So here are these events out there in the world, those little explosions happening, and we're gonna do two things with them. We're gonna store them in this long-term storage here. And that's very likely, we all know that's gonna be a Cassandra cluster, right? Of course. And this is our bounded analysis. Here's data, there's a day of data. I'm gonna go do stuff. What happened on Monday? That's bounded. Relatively high latency analysis. Maybe analyzing Monday takes 5 minutes. I don't know, that's forever. That's a long time. So that is, the keystone is 0 and 0, good, okay. Glad we got that taken care of. That's the top part, the bounded analysis. We will also put these through some sort of event processing framework. Storm is a name that still comes up. Apache Flink, Apache Beam, these are things that are basically APIs for dealing with events. So we'll put those events through that assembly line and probably also through some queue. Usually Kafka shows up right about there. There's a Kafka queue in there that those events go into, and we pull them out. We do some kind of stream processing. The unbounded analysis at low latency. Maybe it takes 5 minutes to analyze Monday. It shouldn't take 5 seconds to get these results. This is famously when 3 people like or retweet or something, 3 people I follow touch some tweet, I get a notification on my phone. Classical stream processing, okay? That's all of the things happening at Twitter, and it says, hey, 3 of Tim's friends did something, I'm gonna tell Tim. So that's not tomorrow, that's minutes or seconds from now. Those results then, of course, are gonna get written into some other kind of database because the Lambda architecture is probably just a part of some bigger system. You've got events happening to you and you use this to deal with them, but what do you do with the events? You do something with them. They're gonna go somewhere. Usually these results are gonna get written into some scalable, low latency read kind of database, put them back into a Cassandra cluster, and then there's some application mobile app, web app, whatever, that lets me see, here's what's going on in my fantasy football league, or overall, here's how this player is performing globally. Oh, whoa, that was a total cultural mismatch. Ask me at lunch if you want to know what fantasy football is. Maybe, yeah, it's a silly thing that Americans do this time of year. Does it happen in Europe? Do you do that with European football? Okay, all right, nice, all right, good. Perfect example then. It was a hit. Yeah, so this will be the application database in an application scaled using one of the two previous techniques. The Lambda processing, the Lambda architecture is just one part of that. So I won't have time to deep dive on any of this stuff, but like I said, there's probably a Kafka, there's probably a Storm. This could very well actually be a Cassandra cluster with Spark. The results could get written into a Cassandra cluster. They could be written into a Postgres or a MySQL if that satisfies the rest of the application also. So just as a basic layout, that's what you might have. Let me skip to, we are not going to talk much about Kafka. I do want to talk about strengths and weaknesses and ratings. The whole theory 4 or 5 years ago when Lambda got started as a paradigm was it's hard to make a system do batch and streaming at the same time, and there are good reasons for that. So this says we're going to build these two subsystems, both of which are optimized for the operational requirements of batch and streaming. Also, key strength of Lambda, good at unbounded data sets. It's kind of a thing that you do with unbounded data sets. Criticism that Lambda is coming under recently is that it's a pain in the butt, because you kind of have to do everything twice. You write your unbounded processing, you write your bounded processing. And people who are actually doing this and maintaining it and operating it over a period of years are actually kind of starting to say, hold up, maybe that's a bad idea. And so some new frameworks are emerging, and Beam and Flink. Beam, I think, is incubating at Apache. I think Flink is top level. The idea behind those two frameworks is to attempt to bring a common API to the bounded and unbounded processing. So I only have to write code once, and it gets executed in my Storm and my Spark or whatever happens there. That's the basic idea there. We're trying to kind of pull that back in because experience has showed that nobody really likes doing that. Also, it doesn't really do mutable update in place data like a conventional database. So this is the stream processing component of a larger system. And also for your reference later, Beam, Storm, and Kafka. Those are the things that I talked about. Okay, scalability. Yep, scales real well. It really only scales for events. It doesn't scale for update in place data. Is still fairly hip. Maybe 2 years ago, this would have been a 4 or a 5, but starting to come under some criticism for maintenance issues, and that being that it's hard. So it gets a 5. All right, 4 minutes, my friends. So sorry. Maybe I'll go over by 1 minute because we started a minute late. Fair? All right, good enough. All right, I appreciate your patience. Okay, so the new serverless note empty racks. Okay, we don't need them anymore. Here's the thing: actual computing does take place on computers, so don't misunderstand this term. What they mean is you don't have to deploy an application server. You don't maintain, here is this computer with this IP address running this process that will answer requests. That's the thing that is a server that you're doing without. What this really is functions as a service. Super hip, super interesting idea, kind of extreme microservices is the way I would think of this. It's microservice thinking taken to the platform and API level such that you just don't have a choice except writing microservices. If you're going to do microservices in Spring, You can also do any kind of other naughtiness you might possibly think of. You could build big monoliths. With the current serverless thinking, you actually just can't. So if you would take this, we'll start with this again, React and Node and a conventional database, and scale the clients, so we start to stress the system. We think, all right, we can scale Node a little bit, so I'll scale my database, do the right thing there, good, good. Then I'll do a couple more steps and turn that Node application into what are really just functions. So every framework and every language grows its own Sinatra. Now, Sinatra was, boy, when was that new? I guess it's about 10 years old. It grew up around the same time as Rails, and it was a Ruby framework that did a very simple thing. It said, when this HTTP verb happens on this URI, do this code. Just like that. And very lightweight, but very useful for some things. This combination of the AWS API gateway and Amazon Lambda, okay, there's like one place you can do this right now, and that's Amazon, lets you take basically those little functions as if they're Sinatra methods, this URI, this code, and deploy them individually as functions in your infrastructure. And when your front end makes API calls, makes like RESTful API calls to those endpoints, just that function runs. You deploy the function individually, you version the function individually, you get billed for the function individually. And you don't pay for static infrastructure. You pay, there's a certain amount for a number of requests, compute time, data transfer. It's metered really on a request by request basis. And you could have a Lambda that looks like that. It's actually just a function. You do it in Python, do it in Java also, they support those. So yeah, super quick overview here. This is like extreme microservices. It's very new. It has the potential to be cheap. I'm interested in seeing how that works out because I'm always a little suspicious of Amazon in this area. They provide amazing, beautiful, innovative services like this, and wow, it's 2/millionths of a cent for 1 million requests. That's got to be cheap, and I don't know. I don't know. We'll see, right? If you go all in, I think maybe that might not be so true. If you want rigorous microservice discipline, you've got it. That's a strength. And if you build this, guaranteed. Just write it up. You'll get to talk about it. Where's this week? You are in cloud jail. If you do this, you get to run on Amazon anywhere you want, as long as it's Amazon. That I would consider that an architectural weakness at this point, but not everybody would. There are plenty of people who are willing to make that commitment. Another potential weakness is one of the strengths, and that's the rigorous microservice discipline. You really don't have anywhere else to go, right? That's what you got to do. There are frameworks emerging already. No surprise. Serverless is one of them. There is another good Software Engineering Daily interview with this guy. So I encourage you to search the archives and find that. Worth listening to if you want to explore the architecture more. Scalability, I'm going to give it a 4 out of 5. You should be able to scale this like crazy as long as you decompose your application into small, uncoupled, cohesive functions. You should be able to go forever. And if you make your backend a scalable database, you're okay. 5 out of 5. Beards and thick rimmed glasses. This is as hipster as it gets right now. A couple years from now, it'll either be dead or a 3 out of 5. Also, I'd call this super hard. It's a very different way of thinking about your application that you and most of us are not used to. 2% of us probably are actually building code this way right now. So it's going to be tough to get into that mode of like, literally you have no shared state except what's in the database. And other things to talk about, but we are out of time. So let me, where was I going to go? Talked about cloud jail, which is a risk of overcommitting to a single kind of cloud. You don't always want to do that. Talked about lots of tools, just to summarize. Talked about Kafka, Storm, Flink, Beam, various Amazon services, Cassandra, and you wouldn't respect me if I didn't remind you that that's what I do. It's my job to teach you how to use Cassandra and the related DataStax Enterprise technologies. If you want to know more about specifics, we've got great stuff on Spark, Cassandra, and also search, which is a lot of Solr stuff, our search technology. So some decent training materials, some of which even has me in it on academy.datastax.com. Check it out. And with that, I say thank you very much for being here. Have a great show.